work through problem number 2 from divergence theorem, and I'm going to break this into two videos. In the first video, because otherwise it's just going to be too long. In the first video, I'm just going to talk a little bit about the problem and why we want the divergence theorem and how I'm going to solve it without the divergence theorem. And then the second one, I'm going to go through and solve it. So let's start out with problem number 2. I have the function that I'm integrating over a surface, and I have the surface that I'm integrating it over, which describes a cylinder. The cylinder is an xy, in the xy plane with a radius of 2, and the height is given from 0 to h. So the cylinder is sitting in the xy plane going up to a height of h. Now here's what's different than we did before. Up to this point we've had some kind of surface, like maybe a plane, and we integrated some function over the surface over some area in the xy plane. And for these problems, we're going to actually be looking at solids, like three-dimensional solids, like the three parts of a cylinder: the top, the bottom, and the side of the cylinder. So we're going to have to do three different integrations, and that's really the reason for the divergence theorem, to make it easy. So let's take a look at what the three surfaces are and how we'll do it. Then I'll actually go through and solve this in the second video. But at least you'll be set up, and if you want to try it on your own. I'm going to start with the bottom. So for the bottom, and now remember, for surface integrals there's four different formulas depending on what we have. Do we have the surface given as a scalar function? Do we have the surface given as a vector valued form? So for the bottom of the can, or the cylinder, or whatever it is, that's going to be my first surface. I'm going to use second formula from there, the surface f dot n, where n is the normal vector ds. Okay? And I'm going to need, I know what f is. F is given to me. It's 2x negative 2y and z squared. I'm going to need to find the normal vector. And in this case, the normal vector is, if I think about it a little bit, the normal vector is the vector pointing straight down from here. So they're all going to be equal to, the normal vector is going to be equal to negative z in this case. Okay. Now let me take the top vector, because that's top surface, because that's going to be similar. For the top surface, I'm going to do exactly the same thing. I'm going to take the function 2x minus 2y z squared. I'm going to dot product it with the normal vector, and in this case the normal vectors are all going to be equal to k. So when I do that, I'm going to be using 0, 0, k, or 0, 0, negative k in the first case. And then I'll worry about what else I have to do here. Well, there's actually one other thing that will make the work easier later on. What I'm going to be doing is I'm going to be integrating this over the area, and in both cases the area that I'm going to be integrating over is a circle with a radius of 2. So I know the area of the circle is going to be equal to pi r squared, where r is equal to 2, so the area is going to be 4 pi. And now all I need to do is figure out what the function is I'm integrating over that area. Okay? For the side of the can, it's a little bit different. So here's surface 3. I'm going to write that in vector form. So when I solve this, I'm going to use formula 4, and it's going to be the double integral, and I'm going to want to have it in vector form. So u of x and y, v of x and y, and I'm going to dot product that with ru cross rv, ds. So I'm using a different formula for the side of the cat. I'm going to put it in vector form rather than use it the way that they have it up there. And the reason is because it's a different type of surface. It's going to be easier to write that. So as long as I'm at it, I might as well go ahead and figure out what that is. For the third one, going to define, well, let me get this out of the way. I'm going to define r of uv as x 2 cosine u, 2 cosine u, 2 sine of u, v. And there's my vector valued function that I'll be using. And that will go into right here. I'll just need to find out what r cross u and r cross v is. Okay? So once again, when I go through and do these, and I'll set up each one of these integrals so you can follow along, what I'm doing is I'm first going to find the area of the base. I'm sorry, the surface integral over the base, then the surface integral over the top. Those are a little bit easier to see. And then the surface integral over the lateral surface of this can. And that will give me, so I'm going to need to do three different surface integrals in order to get the complete surface integral. What the divergence theorem says, if I take the volume of this and I do a triple integral of the divergence of f, I guess that's over volume, it turns out that it's going to be the same as this. You'll see that this is fairly easy to do. These are more difficult to do. So it's kind of weird to move from a double integral to a volume, but we're going to do that because it's going to be easier for us to solve it. In the same way that Green's theorem made it easier to solve line integrals, or a line integral with 3 or 4 parts you could do as one double integral. Okay, I'm going to stop this video and I'm going to pick it up with, now that I've sort of laid it out, I'm going to do the 3 integrals. I'll set them up and probably solve them in the next video. Okay, well, I hope this helps you a little bit. You know, if you try it on your own, the big picture is this. What are we doing that's different? Well, instead of just taking one surface and integrating a function over it, now we're taking as many as the surface has to be. For example, it could be a sphere with just one, or it could be a cylinder with 3 surfaces, or we could have, I suppose, a pyramid with 4 or 5 different surfaces. And then it gets a lot more difficult because we have to do the integration over each of the surfaces. Okay, I'm stopping it here.